So, I am going to be talking about linear programming. Is this size big enough? Is it visible at the back? It's okay? Yeah, okay. So, I am going to start off with linear programming and then gradually while discussing the solution techniques there, move over towards more and more of geometry, coordinate geometry. And let us start with 2 dimensions. So, this is the type of linear programming that many of you probably teach in your syllabus. So, let me just start off with a question, with an example problem. So, this one question maybe we will return to again and again, an example that I have taken. There is a baker who knows 2 recipes. This baker knows how to bake, let us say knows how to bake brownies, knows how to bake tarts, and there are various ingredients that go into both of these. A couple of common ingredients, they both require flour, they both require butter, they both require many other things. But it turns out that all the other things, sorry, was there a question? No. It turns out that all the other things, there is enough stock in the bakery, but these are limited. So, maybe we want to write something like this. The available amounts. So, this baker has maybe 5 kilos of flour and this baker has 1 kilo of butter, and to make one brownie it requires, let us say 200 grams of this and 25 grams of butter. Making tarts is more intensive in butter, it uses 50 grams of butter, but it uses only 100 grams of flour. And now you can imagine what the question is. The question is, what should the baker decide to do? You know, how many brownies, how many tarts, and what is this going to depend on? So, the typical way in which we would solve this would be to say that let us assume that the baker makes x brownies. So, number of brownies is x, number of tarts is y, and now the baker has to figure out how much of each he can make. So, as a thought experiment, we should imagine that at one time only one of these ingredients is limited. Remember, there are other ingredients also in the recipe, and we have said that the other ingredients are available in unlimited amounts. So, let us assume for now that only the flour is limited, there is lots of butter. Then how many brownies can be made and how many tarts can be made? Well, each brownie we know uses 200 grams and each tart uses 100 grams of flour. So, this total had better be less than or equal to the total amount that is available, which is in grams, it is 5,000. So, let us simplify this and write it as 2x plus y is less than or equal to 50. Okay. So, this is a constraint. Right? The baker, no matter what the baker chooses to do, the baker cannot choose values of x and y which make this statement false, simply because there isn't enough of the raw material available. There is going to be a similar constraint for butter, right. So, that is going to be so we have 2 constraints. Now, what do we do with this? So, like I said, the baker has to figure out values of x and y, but there has to be something more which guides the baker's choice. For instance, the baker could just say, I do not want to bake today at all, I want a holiday. X and y are both 0, that is perfectly valid, it satisfies these constraints. So, the way the baker is going to choose x and y is going to be based on something that the baker wants to optimize. Typically, that is going to be some cost, right. So, in this example, let us say that the goal is to maximize the number of objects baked. Why would one want to just maximize the number of objects? Presumably, this makes sense assuming that both brownies and tarts cost the same. They sell for the same cost, so it does not matter which of these we produce. but you want to bake as many as possible to get maximum revenue. So in that case, what we are saying here is just maximize x plus y. Okay. So now this is a typical linear programming formulation. So what is given is some set of constraints on some variables. We decide how to choose these variables. So here we have chosen variables x and y to stand for these objects. Depending on the actual application, it may stand for various things. So there are these variables which we choose, and then there are some constraints which tell us that these variables cannot take arbitrary values. They have to lie within a certain range. And then we want to maximize something. To visualize how exactly we are going to go around maximizing this, what we do is we can actually plot number of brownies and number of tarts on this xy plane. So here I have x, which is the number of brownies, y, which is the number of tarts, I'm guessing that these faint lines that I'm drawing are not really visible at the back, so it doesn't matter. When I put down a number, I will also write the number and tell you what that number is. So continuing with the same thing that we started off with here, imagine that there is only one constraint at a time. So if there were unlimited amount of butter and flour was the only constraint, then we saw that this is the equation, this is the constraint that it gives rise to. 2x plus y had better be less than or equal to 50. So one way to see what this corresponds to in the plane is to say, let's assume that the baker just uses up all the flour. The baker is not constrained to use it all up, but let's assume that the baker just uses all the flour. Then there are two extremes that the baker could do. Either make only brownies. In that case, how many brownies could be made? 25. So you could make 25 brownies but 0 tarts if you use up all the flour. Or you could make 50 tarts and not a single brownie. And now when we join these, I hope I join it correctly. Okay, here's this line. What does this line stand for? It stands for the possible values of x and y at which all the flour is used up. Right? So this is saying use up all the flour. Now, like we said, the baker is not obliged to use all the flour. The baker could use less, but cannot use more. So this is the line on which everything is used exactly. This line is dividing the plane into two regions. There's one side here, and this is one region, this is another region. On one side, the baker is going to be using more than the flour available, and on one side, the baker is going to be using less. So we just have to figure out which is which. In this example, it's completely trivial to see that the correct region we want is this, right? If you go beyond this, you are producing even more than 25 brownies, you just don't have enough flour. So you should be going on this side. So we are interested in this region. There's going to be a similar line corresponding to use up all the butter, right? So use up all the butter. If you make only brownies, you will have 40 of them. If you make only tarts, you will have 20 of them. And so the line looks something like this. Okay. This line corresponds to use up all the butter. Again, as in the previous example, the baker does not necessarily have to use all the butter. The baker could use less but not more. And which is the direction for less? It's below the line. Above would involve more butter. So now what this tells us so far is that whatever values of x and y are chosen, whatever number of brownies or tarts the baker finally decides to choose, that point, that the value that the baker chooses x, y, if I plot it on this plane, it must lie below this line. It must lie below this. So it has to lie in this region, okay, bounded by these two things. But there are some other constraints which I didn't write there. X comma y greater than or equal to 0. You can't bake -1 brownies, right? So we should write those constraints also. So x should be greater than or equal to 0, y should be greater than or equal to 0. And corresponding to these, again, you will get half planes. Just as each line is actually an equation, right? Use up all the flour was the equation 2x plus y is equal to 50. Okay? Whereas this was an inequality. So the equation gave the line. Similarly, here I have equation x equals 0, here I have the equation y equals 0, I have to stay on this side of the line. I have to stay on this side of the line. So really speaking, the feasible region is just this little space here. Okay. So this part, let's call it the feasible region. It's feasible. What we mean by that is that if I choose a value of xy from this region, it is possible for the baker to bake those many brownies and those many tarts. The amount of ingredients available is enough. Okay. So feasible just means that it is possible to do this. Okay. So now in order to find the feasible region, we did not look at this at all. When the feasible region was just given by the constraints. We had all these constraints and they told us what relations x and y must satisfy amongst themselves. Now we want to maximize this. And how do we go around doing this? There is the so-called corner point method. What the corner point method tells us is, whatever we want to maximize, this is what we are calling the objective function. So the corner point method is saying, find the feasible region. Which in this example we have done. Okay. This is the feasible region. Well, maybe when we say find, let's be a little more explicit. What have we found? It is kind of below this line, so it has some corners. So we have identified this corner, maybe this corner also we should identify as 0, 0. There's one more corner here which should be 20 and 10, okay, 20, 10, yeah. So if the baker bakes 20 brownies and 10 tarts, then in fact the baker uses up all the flour and all the butter. Okay. So we find the feasible region, which what it means is that we have found all the corners of the feasible region. Then we evaluate the objective function at all the corners. And then you pick the best. So here I am just saying pick the best because in this example it was maximized, but sometimes you may want to minimize something else, minimize the cost of producing this. So whatever it is that you want to do, at each corner there is a value associated and you pick the best possible value. That is what the corner point method tells us. In this example, if you look at x plus y at all these corners, then it is best over here at 20, 10. So that is the best that the baker can do. The baker can bake 30 of these objects. Okay. But in order to bake 30 of those objects, this figure is also telling us that it must be the case that there are 20 brownies and 10 tarts. So if the baker tries to bake slightly fewer brownies and says I will compensate by instead baking tarts, well, the baker can do some compensation, but the number will not be as large as 30. So that not only is the maximum 30, it is achieved at only this particular combination. Okay. So the maximum in this example is 30 and it is achieved by taking 20 brownies and 10 tarts and no other way. This is the basic framework in linear programming. So given the whatever is the real life problem, there are all kinds of word problems that you would have seen which arise from, this is a manufacturing example, you want to manufacture and the raw materials are in some short supply. There could be transportation problems, there are so-called diet problems and so on, and they can all be framed like this in terms of some constraints on the amounts of each object that you use. There are typically non-negativity constraints in almost all real life problems, and then there is an objective function that you want to either maximize or minimize. And why is this linear programming? Because all these constraints are linear functions. There are no quadratic functions involved in this. So there is this generic method. What we would like to do is to look at it a little bit more closely to see why this method is true. Okay. In this picture kind of we can see, okay, clearly this is the maximum. If you try out various other values, well, you may need to try out all the values along the way to check that nowhere else are you hitting 30. But we know that this method is correct, but we would like to explore it a little bit more because then it's going to give us some more nice information also.
Suppose in one of the manufacturing
Exactly. Yes. So let me give you another example here with brownies and tarts only. Now I'm going to erase this and write this in a little more compact way. What you're saying is that what if the corner point is fractional? So let's say I have a different baker who does not know how to make brownies but knows how to make bars, and so let's say that so for tarts I had said it was 150. Maybe I should keep my brownies number also here. For what is it that I had said earlier? Brownies use 200 of this and 25 of this, tarts use 150, and let's say bars use 250 and 25. And what is available? 5 kilos of this and 1 kilo of this. So that example which we drew was for tarts and brownies. But suppose I have a baker who does not know this recipe, but knows these two recipes. The first baker did not know bars, then this baker now. So now we have to remove one of those lines. We have to remove the line which corresponded to brownies. The line corresponding to brownies was, it was not really a line corresponding to brownies. We had a variable. So now I have to change these constraints and write them in a different way. It turns out that the amount of butter used by both brownies and bars is the same. So that this is the butter constraint and this is the flour constraint. The butter constraint will not change. Okay? So this line remains the same. But the flour constraint will change. Okay? So this will change to 250x. So now maybe I should say x prime, number of bars. Okay, let's call it x. So this is now a different solution. The number of bars is x. No brownies are being made. Then I need that 250x plus 100y is less than or equal to 5000, which is going to give me 5x plus 2y is less than or equal to 100. Okay. And now if I plot that here, what am I going to get? I am going to get a line which goes through 20, 0 here. If I bake only bars, I can bake 20 of them. If I bake only tarts, I can still make 50. So I get a slightly different line. Okay. So this is the line when I'm using up all the flour, but I'm producing bars and tarts as opposed to brownies and tarts. And in this example, exactly the situation that you mentioned will arise. So we have again found a feasible region. The feasible region is what is now bounded by these two lines and the x-axis and the y-axis. We can find out all the corners. How do we find the corners? You have to find the intersection of these two lines. You can solve those two simultaneous equations or in whichever way. But here now when you end up solving these two equations, you are going to get 15, 12.5. So you can make 15 bars and 12.5 tarts. No baker can make 12.5 tarts. So this is an example where this method seems to fail. Okay? So the corner point method, which normally we say will work in such situations when you have linear constraints and a linear objective function, there is a caveat. It will work provided the solutions that you are looking for are rational, are allowed to be rational or fractions. But if you insist on integral solutions, so now here I am going to add one more constraint, an integrality constraint. An integrality constraint would be that x and y must be coming from the set of integers. Then the corner point method does not work. So it's not enough to just evaluate things at the corners. We actually need to look at a finer grid. In this grid, I only plotted 0, 10, 20. If I plot all the integer points along both the axes and I actually mark out this grid of integer points, you may need to look at all the integer points along the boundary. That's not a good method. So we're not going to look at that now. But you have to keep in mind that if you have a fractional solution, you do have to throw it away. I mean, we are using this method only where fractional solutions are still okay. Okay?
In such case, what you are?
Well, one thing which you could do is to evaluate it along the boundaries. Not just at the corner, but at the integer points on the boundary. So the integer points which are closest to the edge.
You can solve by
You can solve by, so that is exactly integer programming. Linear programming is the relaxed version of integer programming where you throw away this constraint. Okay. Now the point is integer programming in general is much harder than linear programming. So this mathematical formulation which we are giving, which is so nice, it says find a feasible region and look at the corners. This is not a method that works for integer programming. This method works only for linear programming. Okay. So in linear programming, the set of potential solutions, all these constraints, what is the constraint doing to the solution space? You pick any constraint, whether it is this constraint or this constraint or the non-negativity constraint. It looks at the entire plane, draws a line through it and says take one half, take a half plane. So in linear programming, every constraint gives you a half plane. And then you are trying to find a point which is in all these half planes, somehow an intersection of half planes. In integer program, what happens is there is a constraint of this form. This constraint is not giving you a half plane at all, right? So what are the potential points, even if I forget all the remaining constraints, just this constraint which says that x must be an integer. What is the, or let's say x must be a non-negative integer. The potential points it is giving you are integer points. So they are separated from each other, it is not a continuous half plane. Now this corner point method is just not applicable in those cases. Okay? So that is something that you must keep in mind, that this can only work for when each constraint gives you a kind of continuous connected region, and in particular that region in this example is a half plane. Okay, like I said, I would like to go back to this example to see a little bit more about what's happening. So let's get rid of bars again. Let's go back to brownies. Available amounts. What were we maximizing there? We were maximizing the total number. This was what we were trying to maximize. So we said maximize x plus y. So when we are maximizing the total number, it's like saying that basically they both cost the same. So it doesn't matter which we produce. So let me try and put down an actual cost. Okay. So let's say that brownie sells for 25 rupees and a tart also sells for 25 rupees. Okay. In this case, if I want to maximize the amount of money I can make, then what is it that I would, so what is the objective function going to be? It's going to be x plus y. Well, really speaking, it's going to be 25x plus 25y, and you can pull out the 25. You maximize x plus y, you would have maximized this. So now let's look at a slight variant. I mean, there is no reason why the two should cost exactly the same. So let's say I have a cost function which says brownies are slightly cheaper than tarts. So tarts, well, they use more butter, and butter is costlier than flour for whatever reason. So the baker is going to make a bigger profit on tarts. He's going to price them higher and make a bigger profit. Now, if these are the prices at which they are going to sell, then what is it that the baker should try to optimize? 20x plus 30y. That's the money that the baker is going to get. So the baker is no longer interested in just saying what is the maximum number of objects I can bake. We really want to maximize 20x plus 30y, which is like 2x plus 3y. Let's go back to that figure and see what happens with 2x plus 3y. So now let's get rid of that other fractional line that we had.
Excuse me, ma'am. Suppose if the cost is going to be a
Suppose the cost is?
Cost is going to be a brownie is going to be 20 rupees and this is going to be 10 rupees. Then my entire line is going to be my objective function.
So there are going to be many there are going to be many different behaviors depending on how the cost varies, right? So we are going to look at many such examples one by one. So let's start with this one, 20, 30. I will come to your example also. It's also there in the list. Okay. So right now our cost function is 2x plus 3y. Not a cost function, it's a profit function really. So what the corner point method says is evaluate this at all these points and find where it is maximum. Well, it turns out that it is maximum here again, right? So maybe we should also write the best point. The best point is 2010, and here also the best point is 2010. Okay. 2x plus 3y is giving me 70 here, 50 here, 60 here. When will it shift away? So now let me write down a series of cost functions. Let's say tarts become much more profitable. They are also more exotic than brownies and the baker can really hike up the price. Then you want to maximize 20x plus 40y, x plus 2y. The corner point method again says, okay, x plus 2y, evaluate it at all these corners and see where it is maximum. X plus 2y, it's 25 here, it's 40 here, it's also 40 here. Okay. So, okay, now maybe I should use some colored chalk instead of saying here, here, again let's give names to these points. Green is not visible. Okay. There is one more color. Okay. So there's this reddish pink point A, there's the yellow point B, there's the orange point C. And here the optimum was C, was B. Here also the optimum was B. But now when we change the price of tarts to double that of brownies, we find that there are two corners which are equally good, A and B, right?
So in this case, any point on the line joining A and B will be the solution.
So now that we have got two corners with the same cost, which is best, the corner point method, let's add one more step. Actually this step is valid. This step says pick the best. If there are ties, you can break the ties arbitrarily. So there are two corners which are the best, you could pick either of them. But as you point out, not only are either of these acceptable, any point on the edge joining them is also going to be acceptable. It's again going to give exactly the same value. And along that line, you have some integer points, some fractional points. So now if you have got two corners, maybe both those corners are non-fractional and they are the best. But on that edge, if there are integer points, then you know that those integer points are the best. Then you don't have to sit and evaluate at all other integer points just inside the boundary. Okay. Now here, what is the idea that we are using? We are saying, let's find the best, ignoring the fact that the solution should be integers. You find the best. Now if that best turns out to have integer values, you're home. That's exactly what you wanted. Suppose that best turned out to give you some non-integer values. Then what is the best that you can achieve with integer values? It is if at all less than this. It cannot be more than this, right? Because even if I don't insist on integers, I cannot do better than a certain value. Now when I insist on integers, maybe I can do less. So if I am very lucky, I may get a corner which is not an integer solution, but I may get two corners which are equally good. So imagine a situation where I have two corners which are equally good, neither of them is an integer, but along that line there is an integer point. Then you can be sure that that is the best point. So that is one way in which you could handle getting an integer solution even when the corners are not integer, but that will work only when you have an edge. You don't always have an edge. So if you get a corner and that corner is not integral, then you are sunk. Right? But in this example, we actually got two corners, in which case we can vary along the edge joining those two corners and pick whichever point looks good to us. In particular, if we are looking for an integer point, we could pick the integer point. Let's look at one more cost function. In fact, we are going to look at many more. So the price of tarts is going up. Okay. Tarts are now costing, are giving, well, it's not cost, like I said, it's profit really. Tarts are now giving a profit which is 3 times that of brownies. So you would want to maximize x plus 3y. And the corner point method is very quickly going to tell you that this is the best, right? X plus 3y, you get 60 here, you get 50 here, and you get 25 here. So, so in this case, the best is A. So what happened to the optimum value? When we were just maximizing x plus y, the optimum was at B. And then as we changed the relative cost of tart relative to the brownie, the optimum value which was original here started shifting there. But it didn't shift in a very smooth way. For that one cost function which we have written, all these values were optimum. And then when the tart became even more profitable than the brownie compared to that, then it moved to this point. So in fact, we got the entire line AB when the price of the profit for tarts was twice that of brownies. At thrice we got only A. What if it were 2.5 times? What would you expect? So, well, you could use the corner point method and again evaluate at these corners. But maybe we should not just blindly use this method. Let's try and figure out what's happening. When the price of tarts is twice that of brownies, at this point, this is the best, right? When the price of tarts is thrice that of brownies, this is the best. Well, for twice, not only is this best, but this is also best, right? So all of these are equally good. But when I increase the cost of tarts to 3 times, this becomes better. So that increase, it doesn't matter whether I increase it from twice to thrice or whether I increase it from twice to 2.5. As long as I increase the price of tarts relative to that of brownies, this is no longer going to be as good, okay, compared to this, because here you have more tarts. But if this is no longer going to be good, and if we still believe the corner point method, we don't have to think more. The optimum must be A. Okay? It has to be a corner. That's not changing. The question is only which corner, and that's what it's telling us, that as the price of tarts goes up, at this price, tarts is twice as profitable as brownies, A and B are equally good. The moment you increase the price of tarts, one of them is going to lose out. It cannot be that even though you increase the price of profit of one and not the other, they both remain equally good. One of them is going to lose out. We know that if when you go far enough, brownies lose out. That means that if you go even a small amount in that direction, brownies will lose out. Now that's the geometric intuition that we want to get out of this. So far we still haven't thought of why the corner point method works, but just using it and then seeing how the optimum is shifting, we can deduce this kind of result. Let's put down a couple more cost functions. We started off with equal cost, then we said let's say tarts are costlier than brownies, so 20, 30. Now let's go in the other direction. Okay? So let's come to the example which you mentioned. So brownies are 20, but tarts give you a profit of only 10. So you would want to optimize 2x plus y. When they were giving equal profit, this was the optimum. Now brownies are giving much more profit than tarts. You would expect things to shift towards brownies, right? But if you actually evaluate what happens at these corners, what do you get? This is 20, 10. This is 25, 0. So 2x plus y is the same at both these places. It's 50. Right? So we have two optimum solutions here. You have A, sorry, not A, that's B. B and C, yellow and orange. So at what kind of price function or profit function would you expect C to become an optimum point? Increasing the profit of what? You should increase the profit of brownies, because at this point, whether you make, at this point brownies and tarts are giving equal profit, and you notice that in going from B to C, the number of brownies is increasing. In going from B to A, the number of brownies is decreasing. So if you want to go from optimum at B to optimum at C, you should expect brownies to become more profitable. In particular, I think this profit function should work, 30, 10. 30, 10, you would want to optimize 3x plus y. Just use the corner point method and you will see that the optimum is C. Now it is only C, not multiple points. Let's try and think a little bit more. What exactly was going on? I mean, we wrote out so many different possible ways of obtaining profit from these, and then our optimum shifted all over, which is not surprising. Of course, I mean, depending on the profit that you get from a certain object, you will make more or less of that. But the interesting thing is that the feasible region did not change. Right? The feasible region is given only by the availability of the raw materials, the availability of the ingredients. Once you have that, this region is fixed, and now within this region, you are visiting the corners to try and figure out what is your best option. So now, without actually evaluating at these corners, let's try and figure out why is it that the maximum always appears at the corners? Okay. So, that is a method that we are using blindly, but let us try and figure out why this holds. So, for this I am going to need a little bit more board space. So, in general, in this example we have something like this, but in general let us say I have the coordinate axis x and y, and what is the function that we are trying to maximize or minimize? Sometimes it could be minimize also, minimize the cost, maximize the profit, right. What is it that we are trying to optimize? It is a function which looks roughly like ax plus by, right. This is the objective function. The fact that we are in the linear programming domain tells us that the objective function must be a linear function of x and y, so it must look like this. Now, this by itself is not any equation or an inequality, it is just a function of x and y. You give me some particular value, some value let us say d. What are all the points at which ax plus by is exactly equal to d? Suppose I plot all of them, what will I get? A straight line. The locus of all points for which, all points x y for which ax plus by is a particular value d is going to be some straight line. Okay. So, let us say that for instance x plus y or x plus 2y, all of them seem to have negative slope. So, let us say that the line looks like this. Suppose I draw this line. This is the line ax plus by equals d. Now, maybe this is the optimum, maybe this is not, because in this figure I have not even drawn the feasible region. So, we do not know. Even without drawing the feasible region, let us just look at this line. I want to achieve a different objective function value. So, I want to achieve some d prime. Then what are the points which will give me the value d prime? It is going to be the line ax plus by equals d prime. What does that line look like? It has to be parallel to this, right, because it is still ax plus by, the slope is just minus a by b. So, the slope has not changed, only the intercept is changing somehow. So, instead of this line I am going to get something parallel to it, maybe the new line is going to look is going to move in this direction depending on the new value of d. So, maybe here I have ax plus b is equal to d prime, and if I move in, the blue is not really visible. So, let us stick to white. Here I get ax plus by is equal to d double prime.
So, you are drawing isotropic lines.
Well, I am just drawing parallel lines.
It may be useful for to decide whether it is going to be a maximum or minimum by drawing isoprofit lines.
Isoprofit lines, yes. So, what we are drawing is the lines corresponding to a fixed value of the objective function. All points on this line have exactly the same objective. So, the objective function, if we think of it as profit if you are maximizing, or you think of it as cost if you are minimizing, okay, then all the points on a particular line have the same cost or the same profit. So, that is why you can say that it is an isoprofit line or an iso cost line. So, what we are drawing is such lines, and what we are observing is that these lines are necessarily parallel. So, what we could do to visualize why this corner point method works is to say all these lines are anyway parallel. Let me take this line and start somewhere very far away. The feasible region is like this, some small bounded region. Let us say the objective function we are looking at was x plus y, and I start with the line x plus y which is here. So, x plus y is some really tiny number, maybe it is minus 1000. It does not even touch the feasible region. Okay. Now, I take this line and I start moving it. So, I sweep the plane. It is like saying you take a ruler and you move it across the page, but while you move it across the page, make sure that the ruler does not rotate. Maintain its slope. So, take this line and move it parallel to itself. At some point, it will first touch the feasible region. Right? So, right now it is not touching the feasible region at all. As you move it, at some point it will first touch the feasible region. So, if x plus y is equal to 0, it is touching the feasible region at the point 0, 0. Below that, it is not touching it. Continue moving it. At some point, it will leave the feasible region. If I move it beyond this, now again the line is not touching the feasible region. So, what is the shape that we are getting out of all this? We are getting a figure which looks like the feasible region looks like this. It is some kind of polygon, right? Why is the feasible region a polygon? Because all our constraints are linear constraints. So, each constraint is giving you a half plane, right? and you are taking the intersection of the half planes. So, here is one constraint which says stay on the right of this line. Here is another constraint which says stay below this line, another constraint which stay below this line. You put together all those constraints, you will get a region which looks like this. So, this is a polygon. Our so-called isoprofit or isocost lines, we start with a line with that required slope which is completely outside this region, somewhere here. And now you sweep it across the plane, maintaining the slope. So, now there are two positions that are important for us. So, as we sweep this line, like I said, there is a point where it first touches the feasible region. You are moving it in this direction. There is a point where it last touches the feasible region. Beyond this, it no longer touches. Okay. And how is the value of d changing as the line moves? If I start off here with a particular value of d and I move the line, how does d change? It increases or it decreases? Not necessarily. In the case of x plus y equals something, yes, it increases. But that depends on the coefficients of x and y, whether they are positive or negative. So, d is going to change in some way. The important thing is either it increases steadily all the way or it decreases steadily all the way. It can't be that it increases for some time and then decreases. That can't happen, right? So, it is changing in a monotonic way. So, in fact, if I instead of starting with a line which was very far away, let me start with a line which actually cuts the feasible region. Okay. If I start with such a line, then I know that there are these feasible points. It is possible for the baker to bake these many of the brownies and tarts. These are all feasible points, and all these feasible points are giving us a certain profit value. Okay. All of them are giving the same profit value. Now, from this position, I could choose to move left or right. These are two different directions of movement. One of them is going to increase d, one of them is going to decrease d. Depending on whether I want to maximize or minimize, I will move in the appropriate direction. So, you could think of this corner point method in that way, that you take a line which has the same slope, the slope as dictated by the objective function, and you can choose an intercept so that it actually intersects the feasible region. So, somehow identify the feasible region, take a line of the correct slope which cuts through it, and now move that line away from itself while maintaining the slope. At the point where it first reaches, tries to leave the region, those are the points which are in some sense the best. So, if you are trying to maximize and it is increasing in this direction, this is the best. Beyond this, you cannot increase it any further. If you are trying to minimize, then this is the best. If you move the line beyond this, then you are not even in the feasible region. So, we are looking for a point which is in the feasible region, so you cannot go outside this range. So, that tells us why we get corner points. Does it tell us why we could get edges? No, we had this situation of AB or AC, no, BC. How did this situation arise, that both B and C, both the corners B and C were optimal, or both the corners A and B were optimal?
One of the constraint equal to your objective function.
One of the
constraint is equal to objective function.
The constraint is an inequality. The objective function is not an inequality. But there is a relation. So, a little more precisely, what is that?
So, coinciding, the same slope.
The same slope. The same slope, exactly. So, each constraint, it's an inequality. We drew the line by making this an equality. Now, that line had a certain slope. If the objective function also throws up the same slope, then the point where the position where this line leaves the region, it's going to leave it by touching that entire edge. Okay. So, if my supporting, if my objective function were not these yellow lines, but these orange lines, and I start moving it, at this point the orange line comes on top of this edge. I am trying to maximize while going in this direction. Here I had just one point, and then as I moved the line, I got multiple points, all the points along the way. Here I got all the points along this edge, and if I move this line even a tiny epsilon amount beyond that, I get no point. The line no longer touches the feasible region. So, I can get an edge only when the objective function is actually aligned with a particular constraint. The slope of the objective function, so to say, is exactly the same as the slope for some constraint thrown up by the program. Now, this gives rise to the interesting fact that I wanted to pull out. So, at extreme points, what is happening is that this line, the the line with which we are sweeping the plane, the line which has a slope dictated by the objective function. This line becomes in some sense tangent. So maybe I should write it somewhere else. The line becomes tangent to the feasible region. I think now I can get rid of this example. So what are we saying? We have a feasible region. Then we have an objective function. Which looks like ax plus by, and now we sweep the line ax plus by equals d, varying d. Now for some values of d, the line becomes tangent to r. Is it clear what I mean by this? So the tangent is actually not very well defined, right, for a polygon. What is the tangent for this polygon at this point? There is no one tangent, right? I mean, if you take a circle and take any point on the circle, there is exactly one tangent. What do we mean by a tangent? A line which intersects that circle in exactly one point. For a polygon, even if you look at a corner of the polygon, there are any number of tangents, because you can draw so many lines which just barely touch it. But we are interested in lines with a particular slope. So with a particular slope, there is only one tangent, or maybe there is none, right? So depending on the slope we are looking at, if this is the slope I am looking at, then there is a tangent at this point. There is no tangent at this point, because you take the line with that slope which goes through this point, it actually cuts through the region. There is a tangent at this point, there is no tangent at this point. So the moment I fix my slope, I need to give this additional information, which was not necessary when I was considering a circle. Because my feasible region is a polygon, it's in fact a convex polygon. We can talk, and because the region is a convex polygon, and because my objective function is giving me lines of a fixed slope, I can talk of this notion of tangent at a point. And there will be two tangents for this bounded polygon. So if my polygon looks like this, then this is one possible tangent and this is the other possible tangent for this direction of movement. Okay, good. So this is what we can see from pictorially from this figure, and this also tells us now why the corner point method works. Okay? Because you want to maximize the profit, you need to sweep that line to the maximum extent possible without leaving the region. When it leaves the region, it will leave it either at a corner or at an edge. Can it leave the region simultaneously on two edges? That is not possible, right? Two lines intersect at one point and you are looking at a line of a particular slope through that point. It can align with one edge or with the other edge or with neither. It cannot simultaneously align with both those edges. So the optimum cannot sit on two edges. It can sit on one edge or it can sit on just one corner. So let me put this down here, and let's see what we can, how we can go beyond this. So what we have seen through this is that the optimum can occur at one corner, or it can appear at one edge and two corners, the two endpoints of that edge. There is a third possibility which also you have seen in some instances, which is that the optimum is just not defined. Okay? So that can happen when the constraints are such that they don't close up a region at all. Okay? In a typical example like this, that will not happen, but if you just pull out mathematical equations, inequalities and plot the region, maybe you will get a situation like that. Let's try and draw one situation like that. So let's say I have one constraint which says that x must be greater than or equal to 2, so I have to stay on this side of the line. It says that x plus y should be greater than or equal to 5, so I have to stay on this side of the line. Then it says that maybe y should, I have a line like this and I have to stay on the other side of that line. X should be greater than or equal to 0. Okay. Now I have this as my feasible region. There could be a situation where the constraints actually give you this region. Now in this case, is it clear that there is an optimum, or is it always the case that there is no optimum? It again depends on the slope. It depends on what the objective function is. So, for instance, if
But the constraints equations have the same slope, we will not be able to find out the solution space at all.
so you are saying that the feasible region may itself be empty. Okay, so let's draw various such figures and see. Okay. So here I drew one figure without actually writing out the equations, where the feasible region was unbounded. In that direction there was no constraint saying it should be less than something, so it went on. The other example which is being suggested is that maybe I have two constraints which are parallel. So I have one constraint here and I have another constraint here. They don't look parallel, but they are parallel. Okay. So now, does this mean that there is no feasible region? It depends not just on the lines, but on the direction of the inequalities. Right? So for instance, if with these parallel lines, I am insisting that I should be on the right of this and on the left of this, then this entire band is a feasible region. But I may have a constraint which says that I should be left of this line and another constraint which says I should be right of this line, then it is impossible. So parallel constraints alone does not mean that it is infeasible. They should be parallel and the inequality should go in the wrong way.
But in this case, we will not be able to find out the corner points.
In which case? In this case?
When the constraints
When the constraints are
are parallel.
parallel, yes. So if there are only these two constraints, then there is no corner point at all. In that case, what happens to the optimum? So suppose, let me draw this a little more carefully. So let's say that the feasible region is not empty. It is, even though I had parallel lines. Okay. There are only two constraints. So this entire region between these two parallel lines is feasible. There are no corner points at all. So if we believe the corner point method, then there should be no optimum. Can we see why there is no optimum? Yes, why is it unbounded? Everything, so the objective function like we saw was a line of this form, ax plus by equals d, d varies, and as I sweep the line, it never leaves the region, right? So the main reason why the corner point method works is that as I sweep the line corresponding to a fixed objective function value, at some point it enters the region and at some point it leaves the region. But here, let's say my objective function had a slope like this. As I start moving it in this direction, it never leaves the region because the region grows in that direction, continues in that direction. Even if I move it here, it never leaves the region. So you cannot identify a point where if I go beyond this, it is impossible to increase or decrease the objective function. So for an optimum to be defined, it must happen that as you sweep this line, it leaves the region at some point. If it does not leave the region, there is no hope of getting an optimum. The optimum is unbounded. Okay? So this is the main idea I want to make, that you can think of this objective function as a line which is sweeping the plane. Now in this example, also I can think of an objective function as a line sweeping the plane. So let's say that this is my objective function slope. I could move it in this direction or I could move it in this direction. That depends on whether I am maximizing or minimizing the quantity, whatever, this is ax plus by equals d. Now do I want to maximize d or do I want to minimize d? Depend. Now if I move the line in this direction, it is never going to leave the region because the region is unbounded out there. If I move the line in this region, in this direction, it is going to exit the region at this point. Right? So even when the region is unbounded, it is possible that the optimum is defined. For the same objective function, the objective function is something of the form ax plus by, and this is an unbounded region. If of the two, I could be either minimizing this or I could be maximizing this. One of these is defined and one of these is undefined. That's what this sweeping the line idea tells us. Right? And again, if it is defined, the optimum, it will appear either at a single corner or at an edge. It could appear along an edge also. For instance, if the line were parallel to the x-axis, then along these two corners and along that edge, you could get the optimum. Okay, now we want to go a little bit beyond this. So far we were looking at 2 dimensions, there were brownies and tarts, or there were bars and tarts. Now we have a more skilled baker who actually knows how to bake brownies and tarts and bars. Okay. So now you need 3 variables, x number of brownies, y number of tarts, z number of bars, x, y, z. Is the corner point method still valid? What is the corner point method saying? Find the feasible region. So let's examine every step of this and see whether it will work. So what does it mean to say find the feasible region? I am going to have constraints of the same type, but involving the 3 variables. X, if I make x brownies, y tarts and z bars, then the total amount of flour used in each one of these I add up, it should be less than the total quantity. So I am going to have a constraint which looks like something x plus something y plus something z is less than or equal to that 5 kilos or whatever. So there is a constraint corresponding to flour. What does that constraint look like in 3-dimensional space?
If it is going to be a few lines of constraints, then it is difficult to find the feasibility.
Okay, I am hearing some multiple answers. There was something about volume, there was something about skew lines, there was something else which I heard but did not quite catch. Plane. Okay, I heard plane. So plane seems to be the right thing. Let's see, my 3D figure drawing is not very good, so some things will have to be left to your imagination, but I can try. So if I have something which says x plus 2y plus z had better be less than or equal to 5, okay, maybe given the amounts of flour you put it together and it throws up this constraint. Then remember the way we started off even in 2 dimensions was to first plot the point on the x axis, plot the point on the y axis and join them. So here suppose I decide to make only brownies, I say y and z are 0, then x can be 5. If I decide to make only tarts, no brownies or bars, then I can make 2.5 of them, which we know is not a good value, but okay. And if I decide to make only tarts, I can make 5 of them. I have got these 3 points. What do I do with these 3 points? So remember what we did in 2 dimensions? We had a constraint which said something like x plus 2y is less than or equal to 5. Then we said x 5, y 2.5, and this was my bounding line, right? One side of it was the half plane that we were interested in. In 3 dimensions, I have got hold of these 3 points. What can I do with the 3 points? I can bring a plane which touches those 3 points. So that plane is going to look like this. Okay. So I've drawn a triangle, but this is a triangle, and now I can extend the triangle in all directions to get the plane. What this constraint says is that whatever that plane is, I have to be below that plane. Well, let's assume for now that x, y, z still have to be non-negative. So I have to be in front of the board and right of this and above this and so on. But also I have to be below that triangle. So now that gives you a feasible region. The feasible region is now a solid region. It's not like a line or a polygon. It's a solid region. But each constraint is corresponding to a plane. And just as the line divided the plane into half planes, the plane is going to divide this space into half spaces. Okay. So we have half spaces. Each constraint is giving us a half space. Is my lettering becoming smaller and smaller? It's still visible at the back, no? If you can't see, please let me know. Yeah? Okay. So in 3 dimensions, each constraint is a half space. What's the first step of the corner point method is to find the feasible region. So you have to find all these half spaces. But it was not just find the half spaces. What did we do even in 2 dimensions? We found the corners, right? So what we did was each constraint, if you assumed that the constraint was tight, you got a line. We took these lines, we looked at their intersections, and we found those points of intersection. Now here, I can't just take 2 planes and find their point of intersection. 2 planes will intersect along a line. So if I want corners, I need to do something more. So we did not write that there explicitly, but when we said find feasible regions, what we really meant was identify the corners. So in 3 dimensions also we need to identify the corners. How will you identify the corners? You will take 3 planes at a time. 2 planes intersect on a line. Here's one plane and here's another plane, they intersect along the line. But I want one point. Now, if I have a third plane, another constraint like this, that plane will cut this line at one point, and that's a corner. That's possibly a corner. Okay. So, maybe we need to look at 3 constraints at a time, put them together, and then you will get some corner points and build up your list of corner points. The next step of the corner point method is to say evaluate the objective function just at these points and take the best. So, what do we expect? Will that still hold in 3 dimensions? So, we should look at a reasoning. Instead of just looking at the way we applied the method, we also reasoned out why did the method work? Because the objective function was a line which swept through the plane. In some sense, all the points with the same objective function value, they formed an isoprofit line. In 3 dimensions, what do they form? An isoprofit plane. All the points which have a particular objective function value d, they form a plane. What can you do with a plane? Now, this is 3 dimensions and I have a plane, I can move it parallel to itself. So, if I have this sheet of paper, I am not allowed to turn it. If it is like this, it has to move in exactly the same way. But once I decide that this is what I am going to do with my plane, the rest of the reasoning is exactly the same. You have a feasible region, your plane is sweeping through space, at some point it will enter the region and at some point it will leave the region. So, we would like to generalize this notion of tangent. Now, in 2 dimensions already we said even though we had these polygons and corners, you can come up with an idea with some notion of tangent. In 3 dimensions, what would be the corresponding analog of a tangent? A plane, it should be tangent to this region which is formed by half spaces, it just touches it, right. So, just touches it, let us formalize. If it touches it at just one point, of course, it is tangent. But there could be other things that happen. It could touch it along a line. Even in 2 dimensions, we saw that you could have tangents which touched an entire edge of the polygon. Those are also tangents. Can anything more happen? It could touch an entire face. So, maybe now we need to look at a solid object. This is a small object, but here is an object and let us say it is placed this way and my new plane is coming in this way, where it touches this entire surface, it is tangent on the entire surface. And that can happen in 3 dimensions. So, if that can happen, then interesting things happen with respect to finding the optimum. So, face is something that we kind of used this terminology without quite defining, but I think it is clear enough. So, a tangent plane. So, a tangent plane, it barely touches the feasible region, where the feasible region is the intersection of half spaces. For other types of regions, this is not going to work. Right? If the feasible region is the intersection of half spaces, then the tangent plane, the way we have defined it, it barely touches it. At how many points can it touch it? It could touch it at one point, a corner. It could touch it along an edge, in which case it touches it at 2 corners. It could touch it at a face. Okay. In fact, this is a kind of circular definition. The face itself is giving you the tangent plane. How do you define the face of a solid object? It is in some sense this tangent plane that we are talking about. I have not given a formal definition, I am just trying to give the intuition, right. So, this tangent plane could be an entire face. In that case, how many corners? It depends upon the face. The number of corners could be arbitrarily large, even though, so it is not as if from 2D you went to 3D and so the number of points at which, corners at which you get the optimum goes from 2 to 3. The number of points at which, the number of corners at which you get the optimum could become huge. So, I could have a figure which looks like this, okay. Some such pyramid, and maybe the optimum is all along the bottom face. The bottom face has so many corners. So, that is not really related to the dimension at all. So, that is one of the complexities of linear programming, that the number of corner points increases can increase very fast, and you would therefore you need a more efficient way of finding which are the corners which are likely to give the optimum. Now, that is not what I want to talk about. Now, I want to look at something slightly different. Sorry, there was a question? No. So, if the optimum in the case of 3 dimensions appears at multiple corners, then what we can say is that all those corners must be coplanar. That is the point that we would like to make. In 2 dimensions, the optimum could appear at 1 corner or at 2 corners. But if it appears at 2 corners, those 2 corners are necessarily connected by an edge of the feasible region. So, it cannot happen that my feasible region is like this and the optimum is appearing here and here. That is not possible. If it appears at 2 corners, those 2 corners must be adjacent along an edge. The same thing in 3 dimension, if the optimum appears at multiple corners, all those corners must be on the same phase, they must all be coplanar. We know that 3 points may determine the plane, but I may have 10 points which are corner points, all 10 of those must necessarily be coplanar. Now, that is something that we can do. So, it comes out simply because of the fact that the objective function at a certain value gives a plane and the plane is sweeping through space. So, now there is an interesting thing that we can pull out of this. So, all along we have been, well, not all along, I used it right in the beginning and then probably not after that. So, we said that the feasible region is a convex region. So, what do we mean by a convex region? So, R is some subset of, let us say in 2 dimensions, what do we mean by convex region? Take any 2 points, the line joining them should lie completely inside. So, this figure is not convex because if I take this point and this point, the line joining them briefly leaves the region and then re-enters. Okay. So, that is our definition of convex region. Now, I can do the following because this entire corner point method seems to be geared towards looking only at corners. But if I take only the set of corners, that is obviously not a convex region. It's a finite set, whereas these are continuous regions which have infinitely many points. So, let us say P is a set of finite points, P1, P2, Pk. Maybe it is the set of corners from my feasible region. Based on this set of points, can I somehow define a convex region? So, now we are doing a reverse engineering. From the feasible region we went to corners, now can we do the opposite, go from a set of points to a convex region for which these are the corners. Can we always do that? So, let us stick to 2 dimensions. Okay. So, example 1, P1 and P2, suppose I have 2 points. Can I define a convex region in 2 dimensions for which these 2 points are corners and there are no other corners? Okay. So, I am going to call that CH, convex hull. It should be a convex region whose corners come from this set. And I am trying to give you an example with 2 points. What would be the convex hull of these 2 points? Not clear. I need to write bigger. Yeah. So, the convex hull, so P is a set of finite points. The convex hull of P is a convex region whose corners are in P. And now I am asking you what would be the convex hull of 2 points. So, for instance, I mean, let us just try and I need to include these 2 points. If I take something like this is a convex region, these 2 points are corners, but there are some other corners also, we do not want that. These 2 should be the only corners. So, what should we do? We should just take this line and nothing else. If you take just the line segment P1, P2, that is convex. It is a convex region by that definition of convex, and its corner points are exactly P1 and P2. Okay. What if I have 3 points? If the 3 points are like this and they are all collinear, then again the convex hull is going to be the line segment which joins these three. But what if they are not collinear? Then it's this triangle, everything inside. Okay. Now let's put down a careful definition and see how it maps to this. So the convex hull, in fact, formally the way one would define it, the convex hull of a set of points is all points P which can be expressed as combinations of the points in this point set. For some A1, what is P? P is P1 to Pk, A1 to Ak with each Ai greater than or equal to 0 and summation Ai equals 1, it turns out that summation Ai Pi is exactly the set P. This is now a definition I seem to have pulled out of the hat, but this is the standard definition of convex combination. Right? So, the convex hull of P is all points small p which can be expressed as a convex combination of these points. What do I mean by convex combination? You take some A1 times P1, A2 times P2, A3 times P3, AK times Pk, and when you add up you get exactly P. But this A1, A2 to AK have to satisfy one additional property. They should all be non-negative and they should add up to 1. And is it clear that that gives you this line? So, if I had just 2 points, P1, P2, let me take A1 equals 1 and A2 equals 0 in that definition. What will I get? I will get the point P1, right? A1, so A1, A2, if I take 1, 0, I get P1. If I take 0, 1, so I am taking no part of P1 but one part of P2, I get P2. What if I take half of P1 and half of P2? The midpoint, that is the midpoint formula. 1/3 of P1, 2/3 of P2, the point which is, you know the section formula, right. So, it is on the line segment P1, P2 twice as close to P1 as to P2. What if I take 2 times P1 and minus 1 times P2? 2 and minus 1 still add up to 1, but now it is no longer on the line, it has gone beyond this region. So here you are getting negative values for one of the two, here you are getting negative, so A2 is negative here, A1 is negative here. In this region, this is exactly the region where both A1 and A2 lie between 0 and 1. For a line segment, it is very easy to see. The point which I am trying to make is that even for an arbitrary point set, let us say I have 10 points like this, they may not necessarily be arranged like this in a polygon, you know, some points drawn out like this. The convex hull defined in this way is exactly the region that you get by visualizing it like this. What is this visualization? It is like, maybe imagine it this way, that I have instead of drawing the plane on the board, let us say this is my plane on which I mark out those points, I put sticks at each of these points. I have the plane, I put these sticks, now I put a rubber band around. So, the rubber band should somehow enclose all the sticks, but when I release the rubber band, it will cover the smallest possible area and it will actually form this polygon. Now, that rubber band may not touch all the points at all. Which are the points it will touch? The corner points. Okay. Now, what we are saying is that that shape that rubber band forms is exactly the set of points which can be expressed like this. So, every point here can be expressed as a convex combination of its corners. You do not need the internal points at all. That is not very hard to prove, but I will not even prove that now. I want to observe something more. Here is this polygon. By this discussion that we had now, which was not very formal, every point inside this can be expressed as a convex combination of its corners, right. But do I really need all the corners to make that convex combination? I want to write this, so this is my point P, I want to find some A1, A2, AK such that that combination of these points gives this. Do I need to use all the corners? How many do I need to use? 2. Okay. So, if this were my point, then in fact it is just a combination of these two. If this were my point, then it is a combination of these two. If this were my point, it is a combination of these two. If this were my point, maybe these two work. Okay. If this were my point, 2 corners do not work. Okay, another example where two corners don't work. Maybe my convex region was just this. And here is the point. The rubber band is taking the shape of the triangle. I have a point inside. I want to write it as a convex combination of the corners of the triangle. It turns out that you can always do that. And you will need to use all three corners of the triangle. You can't use only two of them because it's not on an edge. Right? So you will need three. Now can we go beyond triangle to a more complicated figure where you need more than three? No, we saw an example where 2 is not enough, you need 3. Now give an example where you need 4. Draw what? Let me draw the convex hull of P. The convex hull must always look like a convex polygon, right? It must look like something like this. Okay. Any point inside. Now, can we draw this shape in such a way that to express this point I need 4 corners? I cannot do it with 3 corners. It turns out that you cannot draw such a shape. 3 points will always be enough. One very easy way to see that is to take this polygon and to cut it up into triangles. Start at any one point and just start chopping off triangles. Now every point in the interior lies in exactly one of these triangles. Okay, if it's on the edge, it lies in both, so it lies in at least one triangle. Fix such a triangle. Now this point lies inside this triangle, it can be expressed as a combination of these 3 corners. Okay. So this is something which again in 2D it's very easy to see, but what would be the analog in 3D? We already saw, I erased that just now, that in the linear programming example, when you go from 2D to 3D, the optimum which in 2D could occur at most 2 corners, suddenly it can occur at many corners in 3D. So now the same idea, if I have P which is a set of points in 3-dimensional space. So I want to say that each point in convex hull of P can be expressed as a convex combination of how many corners? It's very tempting to say that the answer should be 4, right? In 2 dimensions, 3 corners were enough. In 3 dimensions, will 4 corners always be enough? So we saw one example where this intuition of increasing by 1 does not work. The linear programming example where the optimum, suddenly we could hit the optimum at multiple corners. So we want to ask whether here the correct answer is 4. It turns out that indeed the answer is 4. And I'm not going to prove this, I would just like to give you a little bit more intuition about what is happening. The convex hull of P in 3 dimensions, it's some polyhedral region, meaning it's some solid region where all the boundaries are faces, right? Straight faces. There are no parts of a sphere or something, straight faces. Okay? So this is this convex region. And now I take any point inside, then I claim that you can identify 4 points and it's a combination of that. But if you take just 4 points anywhere in space, what kind of region do they give you? We saw one example where we took 4 points, where we took 3, that gave a triangle, but if I additionally also had the origin, then that would give a solid figure, right? So what kind of a figure is this? It's a tetrahedron. It has 4 faces. Each face is a triangle. Such figures, such solids are exactly what are called simplices. They are the simplices in 3 dimensions. In fact, this statement we can strengthen a little bit more. This statement is true, but what is also true is the following. CHP can be cut up into tetrahedra by making straight face cuts. So I take this whatever solid region that I have which has straight faces, and I am allowed to use only planar cuts. I can't take a knife and start like this and then bend the knife half. No, cut only along a plane. Not only that, by cutting planes that pass through 3 corners. Three corners determine a plane. I take these 3 corners, I take the plane through them and I cut. Now there is always a way of choosing this which completely splits this solid figure into tetrahedra. For 2 dimensions, it was very easy to see. Straight line cuts split up the polygon into triangles. In 3 dimensions, just imagine a box, and you have to cut the box into tetrahedra and no other shape. So, I would like you to go back and think about how to do this. I have a set of tetrahedra here which you can assemble during the tea break if you want and form the cube. But indeed it is true, and this is in fact a very nice 3D geometry project that could be given to school children also. Ways of cutting up the cube into shapes which are, in some sense, all the shapes are identical. If you have the perfectly balanced cube, that you can cut it into 6 tetrahedra, all the tetrahedra are identical to each other and they can be assembled into the cube. So, like I said, I have these cubes here, I will just take them out, but okay, I will stop my talk here. If there are any questions, I would be happy to take them.